In this lab, we're going to be studying the deflection of charged particles due to electric fields. So your goals for this lab, you're going to observe the deflection of charged particles between plates at different potentials. So it's a relation between electric potential and electric field and motion of a charged particle. And you're going to calculate the ratio of the plate length, which this is called L, to the plate separation, lowercase d. So the electric field is the force per unit charge. Or you can think about it as the direction A plus charge feels a force. And that should be, quotes, feels a force. So which means if you use Newton's second law, you get F equals ma. Rearranging this equation, you get QE equals ma, which then goes to acceleration is equal to QE over A. Which means if you have a charged particle in an electric field, it will accelerate, or its velocity will change. So the next concept, and we're talking about this, is electric potential. So this is the energy per charge. So if we look at this last semester, we talked about work. And then work changes energy, so work and energy have the same units. And this work was equal to a force times a distance. So if we look at this, we're going to get voltage, or your change in voltage, equals electric field. So this is energy per charge equals the force per charge times a change in x, a change in distance. So what's going to happen here, your plates are at different voltages. They're separated by some distance. It creates an electric field between plates. So if we have plate here, plus, minus, let's say this is 500 volts, and this is 0 volts, or the ground, you would set up an electric field going this way. Electric field between the plates. So the way this works in a lab, you have some particle going this way. It's going to go between these plates at, I'm just plugging in 500 volts, 0 volts. There's an electric field going this way. This particle, we'll assume this is a plus particle, its motion is going to be deflected. So its velocity will change. So this is what your setup is. This is a cathode ray tube, CRT, which shoots charged particles at this screen, and when it hits them, they glow. The box on the left controls your accelerating voltage, and this box on the right controls your deflection voltages. So the box on the left makes these particles go through the plate faster. The box on the right increases the voltage between the plates so they'll deflect more. So here is your schematic. This is a side view. These are the horizontal deflection plates. So your particle is going to come in here. It gets accelerated through here. These are the dimensions of your horizontal deflection plates. So if we zoom in on these, we zoom in on this, you will change the deflection, or the voltage, across here. Your particle comes in, and it'll deflect. If you have a higher accelerating voltage, the box on the left, your particle has a bigger, we'll call this the z direction, bigger z component. It spends less time between the plates, and if it's going faster, it's harder to deflect because it spends less time between these plates. So higher Vz, this is harder to deflect because it spends less time in between the plates. If it spends more time, it'll accelerate more because it experiences the force for a longer time. Wait a minute. Force times time? Well, that's a change in momentum. All these first semester concepts just showing up left and right. It's almost like we planned it. This is a close-up of the box on the left, and we're going to take a look at how to read it. First off, let me tell you something. There is a power button right here. This is the power button. This flips it on. This is the standby button. You have to have them both on for it to work. Of potential importance, you need to watch these two knobs right through here and pay real close attention to these colored bars. So if we look at this, notice the meter. When it faces the black bar, you read the black line scale. When you flip this over, you read the red side. There are two plates that change the voltage. So in order to get your total accelerating voltage, you add the readings. And you're going to do this for 4 different volts. So the goal of this, you've got 4 target voltages on your lab sheet. You want to get as close to that as possible, but they are guidelines. So you adjust these knobs over here so that you can make a nice green dot appear here. So pretty much move these knobs back and forth until you get a nice dot. Run through a run of the experiment with the different deflecting voltages, which we'll explain in just a minute, and then do this again. This is the right side. This is the deflecting voltage. So let's look at this. You will turn this knob right here, and it will increase the voltage. And as you can see, the dot that started right here moved over this way as this went up. Eventually this will max out. So what you have to do is flip off the power, which turn this off. This is a power switch. Flip that off, safety first. Flip that probe, which flips the deflecting plates positive and negative. And now you can get your dot to go the other way. So this is the course adjustment. And what you want to do is you want to line this dot along each of these little 1/4 inch lines. 1/4 inch. And then when you flip the plug, you flip the sign on your data table. Okay? Flip the sign on your data table. Just so you can keep what's positive and negative. We'll show you why in a minute. This right here is your fine adjustment. So this changes the scale. So this is your scale, and this is your fine adjustment. When you're taking your readings, this scale is a little funny. This is the deflector again. So if you look right here, if the numbers are black, you read the black scale. If the numbers are red, you read the red scale. And the only one that's a little funky is this really last thing, because it's red, so you'll read the red line, but you multiply everything by 0.1. So instead of being 0 to 50, it's 0 to 5, or 0.5 to 5. So this sets up your big scale, and then this moves the dot. It's like you're fine-tuning. So you'll use this to figure this out. Also remember, read between the lines. Read between the lines. You want to get as accurate as possible. Key points. Watch the color of your dial. That really matters. Also, there's a lot of weird math in this lab. It's not weird, it's just you've got to work through it. Please read your handout and follow it, and ask questions if you have them. Please ask questions. The bottom line is that lower, I'm going to call this accelerating voltage, lower VZ goes to less voltage across the deflector to accelerate. And this is just because when it's going faster, because of your accelerating voltage, it spends less time between the plates. So let's look at some sample data. You will have 4 copies of this table, and your table is going to be bigger. I just wanted to zoom in. So let's say your deflecting voltage to hit the 1/4 inch line is 3 volts. To hit 0, you had to have it at -2. Why is this a minus? Because you had to flip the plug. So if you flip the plug, you flip the sign on the voltage. And then we'll say that this is minus 7.5. In a perfect world, if you didn't apply any voltage, it should go dead center of the screen. So this would be 0. How did you get this to 0? Well, minus 2 to 0 is plus 2. So you add 2 to everything. This becomes 5, and this becomes minus 5.5. So if we move this up here, what you're going to do, you will have 8 values because your table goes all the way up. So you're going to average the values at a 1/4 inch. And you will average your VD adjusted, your adjusted deflecting voltages, and the absolute value. So this would be at 1/4 at D equals 1/4 inch. Your deflecting voltage is equal to 5.25 volts. Once you have this value, you will get your Z value from your schematic that we've shown out. Z is the distance from the deflecting plate to the screen. You will calculate L over D equals some number, which means for each of these tables, you will get 4 values per table. This is a lot of numbers. Good news is you're going to have 16 values. So how do you find error when you have 16 values? I'll let you think about it. Think back to what we did in lab when we had more than 10 values. First semester lab. Looking back, you're going to average the deflecting voltage at each value of your deflection. That's capital D. You'll calculate for those values at each table. Read your lab handout because it goes into detail about how to do this. And there's a lot of math. Then what you're going to do is you will average all of the above to find L over D and compare it to the actual value. Well, how do you get the actual value? Looking at your schematic, you see that these plates are flared. That's because if you come in here and you deflect, you don't want to run into the side. So the goal of this lab is to find L, the length of the plates, to the deflection, an effective value. And I say effective because if you average this big number, your L over D value gets too small because D is too big. If you're right here, your separation distance is too small. So your L over D value is too big. So you need to come up with a way of averaging. And I would recommend a weighted average. And I would look at this up. Weighted averages just account for the fact that this side's bigger than this side. And you'd also need to figure out something like right in here, because these are just straight lines. So you find an effective separation distance for here, find an effective separation distance here, and then figure out what percent this is of that. It's a lot like calculating a grade. So say this is 60% of an exam. So we'll say that homework is 10%, and then tests are 90%. And you get an 80 on homework and a 100% on tests. Well, how would you calculate your grade? You would multiply these two and then add them together. Oh, so this would be 0.9 times 100% and 0.1 times 80%, and you would come up with your final grade, which is another weighted average of just 90. Oh, move that up so I can actually see it. 98%. So you use weighted averages all the time. It's just a matter of figuring it out, and I would be more than happy to work with you on that. In conclusion, you are trying to observe how a charged particle's motion, that needs an apostrophe, is affected by an electric field. You complete 4 tables for different accelerating voltages, and then you calculate L over D for the apparatus. So the L, length of the plates, over D, the separation. If you have any questions, just let me know, and I will see you in lab.